How's it going, guys? So today we are going to do the basics of plotting unit step response. So this is for MBB 410 students, sorry, at the University of Pretoria, mechanical engineering. Okay, so first I'm going to show you some basics of Jupyter Notebook that you might not know. So this can sometimes take up a lot of space, especially if you start zooming in. Okay, so what you can do here is you can say view toggle header and view toggle toolbar, so that'll get rid of those two, and you can always bring them back using the view. I like to keep the header out and the toolbar in because I use cut often and I use add often, and you can even copy cells. So we are going to do plotting of a unit step response and building of transfer functions in Python. So first of all, you want to import your modules numpy as np. From numpy you can import poly1d that we're going to use to build transfer functions. Control is ct, matplotlib.pyplot is plt, and you don't need this last one. Let's edit that one out. Okay, so now below are called magics. You use a percentage sign, matplotlib qt or matplotlib notebook, so they're each going to give you a different thing. If you use matplotlib qt5 and shift enter runs the cell, when you plot something, so let's quickly do this and go down to this. Okay, that's going to bring it up in a new figure, you see. So this figure is not in the notebook, it's an additional figure. The matplotlib notebook does something else. Note that if I run this cell here, shift enter, it says warning, cannot change a different GUI toolkit. This is because once you've run a magic, you can't run another magic for matplotlib.notebook. The way to change it is you go kernel, restart, and it restarts the whole kernel, and I think it's done. Yeah, there it's done, and we'd run this cell again, and now you'd run notebook. So shift enter, and now when we do that again, and we'll go over all this code now. Shift enter. I'm just showing you there. Can you see that it's in the notebook? So it's here. Okay, cool. So I prefer to use the Qt5 for various reasons, but yeah. So let's quickly restart the kernel and rerun this bugger here. Okay, and run the Qt5 and don't run this cell. So now I've mentioned that to switch between the magics. Now drawing the unit step response of a system. First we've got to build the transfer function. So here's the transfer function g. What a transfer function basically is if you have a system, you put an input in, the whole system works, you get an output. So for instance, you press your foot down on the pedal of a car, a whole bunch of mechanical things happen, and you go a certain speed or a certain acceleration. Now this transfer function describes that whole process. You put something in and you get something out. Okay, so now we want to code this. So we can see that there's one polynomial at the top, and it's just a constant, and there's two polynomials at the bottom, s plus 7 and s squared plus 40s plus 1300. So in this case we only have to make polynomials at the bottom because the top is just a constant, and even if there was a polynomial at the top we wouldn't have to make these. So we're going to say g den 1, which is g denominator 1, poly 1d, and then we're going to say 1 and 7. Okay, then number 2 is 1, 40 and 1300, which is here, and that's the two g dens. Then you make the total denominator, which is the two multiplied by each other. That'll give you a polynomial. So now we want this function here, control.transfer function tf, uses lists of constants. So that's why we say gden is equal to gden.c. It pulls the constants of this new big denominator polynomial, and it gives you a list of constants. So now G here we want to define as control the transfer function. The top list is going to be 200 because it's just a constant there, and the bottom is going to be our Gden, our list of constants. Then we print G and we get 200, 200, cool, that's fine. There's an S here and an S squared, which is going to give us an S cubed, so that's right there, and that looks relatively okay, cool. So we've done that. Now let's try a different one. Same thing, 820, here's a polynomial, here's a polynomial. You got Gden 1, Gden 2, okay. Notice that this is just an S. There's no constant term at the end. Therefore we call it 1 and 0. If for instance this was just an S cubed, then it would be 1, 0, 0. You've got to add in the zeros for the terms after, like the S and the constant, otherwise it'll just assume it's a constant. So here we want just an S, cool. That should work, and we've done the same thing here, transfer function, print G, there it is. S and S squared is S cubed, that looks right. Cool, transfer function 3. I'll go through this super quick. There's the S plus 18, we just put it up here. If there was two polynomials at the top, we would have to do this process like we've been doing originally, and have the G num, and have all the two numerators. For instance, if there was two polynomials at the top, you'd have the two numerators times by each other, and G num equals G num dot C. Then we put the whole thing together, and we've got 1, 2, 3, 4, and you've got an S to the 4. Okay, cool. So now we are going to plot the unit step response, what we finally, what the video said we're finally going to do. So these ones don't give that nice of a plot, so we define a new one here, which you don't have to worry about. Yes, and now when we plot the unit step response, you always need to draw the unit step response of the closed loop system. This function is just an open loop transfer function. We need to give it a feedback like this. Okay, so we give our system here that we've defined a feedback by saying system equals ct.feedback of G. The feedback is a unity feedback, that's what the 1 is for, and it's a negative feedback. Note that Python or control.feedback will automatically assume a unit negative feedback. So this line of code here will also work perfectly. But if you have one where it's not a unity feedback and it's not a negative, you have to change them here. So these two do exactly the same thing. They assume a unity feedback, a negative unity feedback, but if it's not, you have to change these two values here. Okay, then our DC gain is the DC gain of the closed loop transfer function. This is the closed loop transfer function here. And then we say PLT, which is what we imported above over here, matplotlib.pyplot as PLT. This is the function that's going to plot for us. Okay, cool. Now tEnd, that is the end here. That's the time which it's going to go to. T is the time that we is the time variable, and it's going to go from 0 to tEnd for 500 steps. This is using np.linspace. Note that you can also use np.arrange. It just uses the first term, the last term, and in steps of 0.01. This uses first term, last term for 500 steps. Okay, cool. Then x and y equals control.step_response of the system and the time variable, and that'll give you two lists of values, which is going to be the lists of values for this graph here. Now we say plt.plot x and y, and then that should give us qt5 here. That should give us this. Cool. So that was literally just plotting this blue response here. That's the unit step response. Now for the percent overshoot, we're going to say plt.hlines, and we're going to say dc gain 1.1. So 1.1, this first term here, DC gain times 1.1, is the magnitude. It's going to be the height here. It's going to be this y value. Okay, and from 0 to t end again, and we just give it a green color. Then this second one, so that's going to be the percent overshoot. This is going to be the settling time bound of 2%. That's why it's 1.02 and 0.98 from 0 to t end, both of them. And then the last one is just going to be the DC gain, which has the horizontal line of a magnitude of DC gain from 0 to t end. Okay, then our settling time we just randomly assign to 1, and now we're going to say plt.v lines, which is vertical lines. These are horizontal lines, these are vertical lines. There is other way to plot lines, which are probably less coding, but I like the H lines and the V lines. It's relatively intuitive. So this is going to be the x-axis magnitude from 0 to DC gain 1.05, and that's going to be the y. So here's the x-axis, which is 1, which is the TS, and it goes from 0 to the DC gain times 1.05. You can make it as long as you want. Those are just the values I use. Okay, so that is plotting the unit step response. Important things to remember are it's always of the closed loop system. So you've got to give it feedback of G. And then some of the other things that's just the basics of Jupyter Notebook is you see these things. Sometimes you might click this and not know what the hell is going on. You just go Shift Enter and you run that cell. This, if you can see, is different. Look here, this is Markdown. You get 4 different options. Generally we have code. These will be Markdown. You can also have raw NB convert, which is just typing, and you can use heading, which will do something. It's just a different kind of Markdown, but I just use Markdown for headings and stuff like that, and for pictures. Okay, so that is going to be all. We covered the magics, we covered creating a transfer function and the different transfer functions, and then we finally covered plotting the unit feedback, plotting the unit step response of the system. Cool, so that's going to be all. Hope it helps. Cheers.